In this video, we will deeply explore Hawking radiation and take a journey into the fascinating physics of black holes. By the end, you will have a clear understanding of what Hawking radiation is and why it plays a crucial role in our understanding of black holes and the universe. If you're passionate about cosmology and physics, you're in the right place. Let me know in the comments where you're watching from, and let's get started. Imagine standing at the edge of the most mysterious object in the entire universe. You are looking at something so strange, so powerful, that it seems to violate the very laws that govern reality itself. This is not science fiction. This is the story of black holes and a discovery that would shake physics to its core. In the early 1970s, physicists faced a problem that kept them awake at night. Black holes, these cosmic monsters that devour everything around them, appeared to do something that should be impossible according to the laws of physics. They seemed to destroy information completely and utterly, erasing it from existence as if it had never been there at all. Now, you might be thinking, what is the big deal about information being destroyed? After all, we destroy information all the time when we delete files from our computers or burn old documents. But here is the thing that makes physicists nervous. In the quantum world, information is not just data on a page or bits in a computer. Information is something far more fundamental. It represents the complete state of every particle, every quantum property, every tiny detail about the physical world. And according to the laws of quantum mechanics, this information can be scrambled, mixed up and hidden, but it can never truly vanish. Think about it this way. If you burn a book, the information in that book is not really destroyed. In principle, if you could track every single atom of smoke, every photon of light, every bit of heat that escaped from that fire, you could reconstruct what was written in that book. The information becomes incredibly difficult to read, scattered across billions of particles, but it still exists somewhere in the universe. This is what physicists mean when they say information is conserved. It can change form, but it cannot disappear. But black holes seem to break this sacred rule. When something falls into a black hole, it crosses a boundary called the event horizon. Beyond this point, nothing can escape, not even light, which is the fastest thing in the universe. Once you cross that line, you are gone forever. And with you goes every bit of information about what you were, where you came from, and what you were made of. The black hole swallows you whole, and the universe has no memory that you ever existed. This created what scientists call a paradox. A paradox is when two things that both seem to be true cannot possibly be true at the same time. On one hand, quantum mechanics says information must be preserved. On the other hand, black holes appear to destroy information completely. Both of these statements come from well-tested theories that have been proven correct thousands of times. Yet they directly contradict each other. Stephen Hawking, a young physicist working at Cambridge University, became obsessed with this problem. He was not content to simply accept that black holes were exceptions to the rules. He wanted to understand what was really happening. Little did anyone know that his investigation would lead to one of the most beautiful and surprising discoveries in the history of physics, a discovery that would reveal black holes are not the eternal prisons everyone thought they were. The stakes could not be higher. If information can truly be destroyed, then the entire framework of quantum mechanics might be wrong. And quantum mechanics is not just some abstract theory. It is the foundation of chemistry, of how atoms bond, of how the sun shines, of how computers work. If quantum mechanics is wrong about something as fundamental as information conservation, then we need to rebuild our understanding of reality from the ground up. But if information cannot be destroyed, then black holes must be doing something far stranger and more subtle than anyone imagined. They must have a secret, a way of preserving information even as they seem to devour everything. Finding this secret would require combining two theories that had never been successfully united, quantum mechanics and Einstein's general relativity. It would require thinking about space and time and matter in completely new ways. This is where our journey begins, at the intersection of the very large and the very small, where the force of gravity becomes so intense that it bends the rules of the quantum world, and where the quantum world fights back in the most unexpected way imaginable. Chapter 2: Building our Toolkit. The physics we need. Before we can understand how Stephen Hawking solved this puzzle, we need to equip ourselves with the right tools. Think of these as the detective's magnifying glass and fingerprint kit, the essential equipment we need to investigate this cosmic mystery. We need to understand three big ideas that will be the foundation for everything that follows. Let us start with quantum mechanics, which is the physics of the very small. When scientists first discovered the quantum world in the early 20th century, they found something shocking. The universe at its tiniest scales does not behave anything like the world we see around us. Down at the level of atoms and particles, reality is fuzzy, probabilistic, and downright weird. In the quantum world, particles do not have definite positions until you measure them. Before you look, an electron exists in a strange state of being in many places at once, what physicists call a superposition. Only when you observe it does it snap into one specific location. Even stranger, particles can tunnel through barriers that should be impossible to cross, appearing on the other side, as if the wall was not even there. And perhaps most bizarre of all, empty space is not empty at all. This last point is crucial for understanding Hawking radiation, so let us spend some time really understanding it. When you look at the vacuum of space, the regions between stars and galaxies where there appears to be nothing, you might think you are looking at perfect emptiness. But according to quantum mechanics, this emptiness is actually seething with activity. Here is why. There is a fundamental principle in quantum mechanics called the Heisenberg uncertainty principle. It tells us that certain pairs of properties cannot both be known precisely at the same time. The more precisely you know one property, the less precisely you can know the other. One version of this principle involves energy and time. It says that for very brief moments, the universe can borrow energy from nowhere, as long as it pays it back quickly enough. Think of it like this. Imagine you have a strict banker who tracks every penny in your account. Normally, you cannot spend money you do not have. But suppose this banker only checks your account once per day. You could borrow $1 in the morning, use it, and pay it back before the evening, and the banker would never know. The uncertainty principle is like that cosmic banker who only checks at specific intervals. As long as the energy is borrowed and returned fast enough, the universe allows it. This energy borrowing has a spectacular consequence. The energy can briefly transform into a pair of particles, a particle and its antimatter twin, which pop into existence out of the vacuum. These are called virtual particles. They appear in pairs because you need both a particle and an antiparticle to have everything balance out properly, charge, momentum, and all the other properties that need to be conserved. These particle pairs exist for only an incredibly short time, typically much less than a trillionth of a second. Then they crash back together, annihilate each other, and the borrowed energy is returned to the vacuum. To us, it looks like nothing happened, but for that brief instant, the vacuum spawned matter and antimatter out of pure energy. Now, this might sound like wild speculation, but these virtual particles have real, measurable effects. There is an experiment called the Casimir effect, where two metal plates are placed very close together in a vacuum. The plates push together with a tiny force, and this force comes from virtual particles. Between the plates, only certain virtual particles with specific wavelengths can exist because they have to fit in the gap. Outside the plates, all wavelengths of virtual particles can exist. This creates an imbalance, a pressure difference, and the plates move together. Scientists have measured this effect in laboratories, confirming that the vacuum really is filled with these quantum fluctuations. The second tool we need is Einstein's general relativity, which is the physics of gravity and space-time. Before Einstein came along, people thought of space as just an empty stage where events happen, and time as a universal clock ticking away in the background. Einstein showed that this picture is completely wrong. Space and time are not separate things. They are woven together into a four-dimensional fabric called space-time. And this fabric is not rigid. It can bend, stretch, and curve. What we call gravity is actually the curvature of space-time caused by mass and energy. Imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a dip in the sheet, and if you roll a marble nearby, it will spiral inward toward the ball. This is similar to how Earth curves space-time around it, and the Moon orbits in that curved space-time. The more mass you concentrate in one place, the more you curve space-time. And if you concentrate enough mass into a small enough region, you can curve space-time so extremely that you create a black hole. At the center of a black hole, the curvature becomes infinite, creating what is called a singularity. But before you even reach that point, there is a boundary called the event horizon. The event horizon is the point of no return. Once anything, matter or light, crosses this boundary, it cannot escape. From the outside, the event horizon looks like a perfect sphere surrounding the black hole. But it is not a physical surface. There is no wall there, no barrier you would bounce off if you touched it. Instead, it is a place where space-time is curved so much that all paths, all possible futures, lead inward toward the singularity. Here is the really mind-bending part about the event horizon. If you watch someone falling toward a black hole, you would see them slow down as they got closer to the horizon. Time itself runs slower in strong gravitational fields, an effect Einstein predicted and that we have measured with atomic clocks. As the person reaches the horizon, from your perspective, they would seem to freeze in time, getting slower and slower, fading from view as their light gets redshifted. You would never actually see them cross the horizon. But from the falling person's perspective, nothing special happens at the horizon. They cross it smoothly in a finite amount of their own time. They would not even notice the exact moment they passed through. It is only later, as they fall toward the singularity, that the tidal forces, the difference in gravitational pull from their head to their feet, would become noticeable and eventually lethal. These two perspectives, the outside observer and the falling observer, both describe the same reality but see completely different things happening. The third tool we need is thermodynamics, the physics of heat, energy, and disorder. Thermodynamics started as a practical science about steam engines, but it revealed deep truths about the universe. The most important concept for our story is entropy, which measures disorder or randomness in a system. The second law of thermodynamics tells us that entropy always increases in a closed system. Things naturally become more disordered over time. A cup of hot coffee left on a table will cool down, spreading its heat energy into the surrounding air, increasing the total disorder of the system. The coffee never spontaneously gets hotter by sucking heat back out of the air, even though this would not violate energy conservation. Why? Because that would decrease entropy, and entropy always increases. Entropy is deeply connected to information. When entropy increases, information becomes harder to access. The information about which specific molecules in the coffee have which specific energies get scrambled and spread out. It is still there in principle, but it becomes practically impossible to recover. A high entropy state is one where you have less information about the specific details of what is going on. Now here is where these three tools come together in a surprising way. In the 1970s, physicists discovered that black holes follow mathematical laws that look exactly like the laws of thermodynamics. They have a quantity that only increases, like entropy. They have a property that acts like temperature. But according to everything we knew then, black holes were perfectly black. They had no temperature, because temperature means you radiate heat, and black holes do not let anything out. Or so everyone thought. This apparent connection between black holes and thermodynamics was seen as just a mathematical curiosity, a strange coincidence. But Stephen Hawking suspected there was something deeper going on, something that would require combining all three of these tools, quantum mechanics, general relativity, and thermodynamics, in a way that had never been done before. Chapter 3. What makes black holes so special? Now that we have our conceptual tools ready, let us focus on black holes themselves and understand why they are such extreme and special objects. Black holes are not just very dense stars or collapsed matter. They represent something far more fundamental, a place where space-time itself is torn and twisted into a new configuration. The story of black holes begins not with observations or experiments, but with mathematics. In 1915, just weeks after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations. Schwarzschild was serving in the German army during World War I, and he did these calculations while stationed on the Russian front. Despite the terrible conditions, he worked through the complex mathematics and found something extraordinary. Schwarzschild discovered that if you compressed enough mass into a small enough region, Einstein's equations predicted the formation of a region from which nothing could escape. At first, physicists did not take this seriously. They thought it was just a mathematical oddity, a strange solution that would never actually occur in nature. Even Einstein himself was skeptical that such objects could really exist. For decades, black holes remained a theoretical curiosity. But as physicists studied them more carefully, they realized these objects were not just possible, but inevitable. When a massive star runs out of fuel, it can no longer support itself against its own gravity. If the star is massive enough, no force in nature is strong enough to stop the collapse. The star implodes, and all its matter gets compressed into a region so small that it creates a black hole. The defining feature of a black hole is the event horizon, and to really understand what makes black holes special, we need to think carefully about what this horizon means. The event horizon is located at what we call the Schwarzschild radius, a distance that depends on the mass of the black hole. For an object with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it would be about 9 millimeters. These objects are obviously not black holes, because their actual matter is spread out over much larger distances, but if you could compress them down past their Schwarzschild radius, they would become black holes. What happens at the event horizon? From far away, it looks like a spherical surface. But as we mentioned before, there is nothing physical there, no membrane or boundary. What makes it special is the geometry of space-time itself. Inside the event horizon, all time-like paths, meaning all possible ways you could move through time, point toward the singularity at the center. Let me try to make this clearer. In normal space, you have freedom to move in any direction. You can go left or right, forward or backward, up or down. Time is different because you can only move forward in time, never backward. Inside an event horizon, falling toward the singularity becomes like moving forward in time. Just as you cannot move backward in time, you cannot move away from the singularity once you're inside. It is not that some force is pulling you in, it is that all possible futures lead in only one direction, inward. This is why we call it an event horizon. It is a horizon beyond which we cannot see events. Light emitted inside the horizon cannot reach us outside because even light traveling at the ultimate speed limit, cannot escape. The horizon marks the boundary of what is causally connected to the rest of the universe. Black holes come in different types based on what properties they have. The simplest kind is called a Schwarzschild black hole, which has mass but no electric charge and no rotation. Real black holes are more complicated. Most are rotating, sometimes very rapidly, and these are called Kerr black holes after the mathematician Roy Kerr, who found the solution. Rotating black holes have two event horizons and a region outside the outer horizon called the ergosphere, where space itself is dragged around by the rotation. The singularity at the center of a black hole is where our understanding breaks down completely. General relativity predicts that all the matter of the collapsed star gets compressed into a single point of infinite density. But physicists do not really believe this. Infinity is usually a sign that your theory has reached its limits, that you need new physics to describe what is really happening. We suspect that quantum mechanics somehow changes the picture at the singularity, but we do not yet have a complete theory of quantum gravity to tell us exactly what happens there. One of the most fascinating aspects of black holes is their effect on time. As you get closer to a black hole, time runs slower relative to someone far away. This is called gravitational time dilation, and it is not just a perception. Time really does pass at different rates depending on how deep you are in a gravitational field. If you could hover just outside the event horizon for an hour and then return to a safe distance, you might find that years or decades had passed for observers far from the black hole. At the event horizon itself, time dilation becomes infinite from the perspective of an outside observer. This leads to a strange conclusion. Imagine a black hole forms from a collapsing star. From our perspective, watching from far away, matter falls toward the forming event horizon, but never quite reaches it. The surface of the collapsing star appears to freeze just above where the horizon will be, getting dimmer and more redshifted, but never crossing. In a sense, from the outside perspective, the black hole never quite finishes forming. Yet, from the perspective of matter falling in, the collapse proceeds smoothly and rapidly. The horizon forms, and the matter falls through it. These two descriptions seem to contradict each other, but they are both correct in their own reference frames. This is one of the strange features of relativity. Different observers can have very different accounts of the same events, and both accounts are equally valid. Black holes also have a strange property relating to information. Imagine you threw a library full of books into a black hole. From the outside, you would see those books freeze and fade at the horizon, but you would lose all the detailed information about what was in them. All you would be able to measure about the black hole afterward is its mass, which increased by the mass of the books, its charge, if the books had net electric charge, and its angular momentum if you threw them in with some spin. Three numbers: mass, charge, and rotation. Everything else, all the trillions of details about what was in those books, seems to be gone. John Wheeler, a famous physicist, summarized this by saying, "Black holes have no hair." This is a metaphor meaning they have no distinguishing features, no details beyond those three basic properties. It is like saying every black hole with the same mass, charge and rotation looks identical from the outside, regardless of what fell in to make it. A black hole made from collapsed stars looks the same as a black hole made from collapsed gas, or from anything else with the same mass, charge and rotation. This no-hair theorem is what makes the information paradox so severe. If black holes truly have no hair, if all the details about what fell in are erased, then where does the information go? This is the question that would drive Hawking to his remarkable discovery. But before we get there, we need to understand what physicists knew about black holes in the early 1970s. Chapter 4. The Classical Black Hole. Problem. By the early 1970s, physicists had developed a sophisticated understanding of black holes using Einstein's general relativity. They knew the mathematics describing how black holes form, how they grow, and how they affect the space around them. But something strange began to emerge from these equations, a set of patterns that looked suspiciously familiar. Jacob Bekenstein was a graduate student working with John Wheeler at Princeton University. Bekenstein was troubled by the apparent violation of the second law of thermodynamics that black holes seem to create. Remember that the second law says entropy, the measure of disorder, always increases in any closed system. But what happens if you throw something with high entropy into a black hole? Imagine you have a room full of gas molecules bouncing around randomly. This gas has high entropy because there are many possible ways to arrange those molecules that would look essentially the same. The information about exactly which molecule is where is very scrambled. Now you throw this gas into a black hole. From the outside, the black hole just gets slightly more massive. All the detailed information about those gas molecules seems to disappear, and with it, all that entropy vanishes from our universe. This appeared to violate the second law of thermodynamics. You could decrease the total entropy of the universe by throwing high-entropy objects into black holes. This troubled Bekenstein deeply because the second law is one of the most solid principles in physics. We have never seen it violated, not once in billions of observations. Bekenstein proposed a radical solution. What if black holes themselves have entropy? What if the missing entropy did not disappear, but was actually absorbed by the black hole, becoming part of the black hole's own entropy? If this were true, the second law could be saved. The total entropy, the entropy of everything outside the black hole, plus the entropy of the black hole itself, would still increase. But how much entropy does a black hole have? Bekenstein argued that it should be proportional to the area of the event horizon. This makes sense in a way. The area of the horizon measures how big the boundary is, and you might think of that boundary as containing or encoding all the information about what fell in. The more area you have, the more information you can store. Stephen Hawking initially thought this idea was nonsense. His objection was simple and powerful. In thermodynamics, any object with entropy must have a temperature. and any object with temperature must radiate energy. But black holes are black. They absorb everything and emit nothing. How could they possibly have a temperature? Along with other physicists, Hawking had discovered what are now called the 4 laws of black hole mechanics. These laws described how black holes behave, and they bore an uncanny resemblance to the laws of thermodynamics. The first law related changes in a black hole's mass to changes in its area and rotation, similar to how the first law of thermodynamics relates energy, heat, and work. The second law said that the total area of all event horizons can never decrease, similar to how entropy never decreases. There was even a third law and a 0th law, all paralleling thermodynamics. But Hawking and his colleagues saw these as purely mathematical analogies. The area of the horizon was like entropy, but it was not actual entropy. The surface gravity of a black hole, a measure of how strong the gravitational pull is at the horizon, was like temperature, but it was not actual temperature. These were just equations that happened to have the same form, nothing more. To understand why Hawking was so confident about this, we need to think about what it would mean for a black hole to have a real temperature. Temperature is fundamentally about random thermal motion. A hot object is one where the atoms or particles in it are jiggling around rapidly. When something has a temperature, it radiates electromagnetic waves, light and heat, and the spectrum of this radiation is related to the temperature. A hot piece of metal glows red, then white, as its temperature increases. This is called blackbody radiation. For a black hole to have a temperature, it would need to emit this kind of thermal radiation. But a black hole, by definition, does not emit anything. This was proven mathematically. Once the event horizon forms, classical physics says that nothing can come out. Zero radiation means zero temperature, means zero entropy. The math was airtight, or so it seemed. There was another problem with the idea of black hole entropy. Entropy is related to the number of possible microscopic states that correspond to the same macroscopic appearance. For a gas, the entropy counts how many ways you could rearrange the molecules while keeping the overall properties like temperature and pressure the same. But what are the microscopic states of a black hole? Black holes have no hair, remember. They look the same from the outside, regardless of what made them. How could something with no internal structure have entropy? Despite these objections, Bekenstein stuck to his guns. He felt that something deep was going on with this connection between black holes and thermodynamics, that it could not be just a coincidence. He even made a specific proposal for the amount of entropy, suggesting it should be proportional to the area of the horizon divided by the square of the Planck length, a fundamental scale in quantum mechanics. But without a mechanism for how black holes could actually radiate, the idea remained controversial. The debate reached an impasse. On one side, the second law of thermodynamics seemed to demand that black holes have entropy. On the other side, the mathematics of general relativity absolutely forbade black holes from radiating. Something had to give, but what? The answer would come from a place that neither side had fully considered. Both Bekenstein and the skeptics were working within the framework of classical physics. Bekenstein was invoking quantum concepts like the Planck length, but not fully including quantum mechanics in the picture. Hawking and others were using general relativity without quantum effects. The breakthrough would require genuinely combining these two theories, letting quantum mechanics and gravity interact in a way that revealed entirely new phenomena. Hawking began to reconsider the problem in late 1973. He started to wonder what would happen if you included quantum effects near the event horizon of a black hole. Not inside the black hole where everything is classical and deterministic, but right at the boundary where the quantum vacuum meets the extreme curvature of space-time. This was uncharted territory. Nobody had done this calculation carefully before because it was fiendishly difficult, requiring techniques from both quantum field theory and general relativity. What Hawking was about to discover would shock him and everyone else. It would prove that Bekenstein was right about black holes having entropy and temperature, but for reasons nobody had imagined. It would reveal that quantum mechanics turns the impenetrable prison of a black hole into something far stranger, an object that slowly evaporates, that leaks energy back into the universe, and that eventually might disappear completely. The discovery would raise as many questions as it answered, and those questions remain at the frontier of physics today. Chapter 5. The Quantum Vacuum and Virtual Particles. To understand Hawking's breakthrough, we need to dive deeper into the quantum nature of empty space. We touched on this concept earlier, but now we need to really understand it at a fundamental level, because it is the key to everything that follows. Let us start with a thought experiment. Imagine you have a perfect vacuum, a region of space where you have removed every single particle, every atom, every bit of matter and radiation. You might think you are left with nothing, just empty space. But quantum mechanics says this intuition is completely wrong. The reason goes back to the Heisenberg uncertainty principle that we discussed earlier. This principle is not just about measurement or our knowledge. It is a fundamental feature of reality itself. The principle says that certain pairs of quantities cannot both be precisely defined at the same time. The most famous version involves position and momentum. You cannot know both exactly where a particle is and exactly how fast it is moving. But there is another version that involves energy and time. This energy-time uncertainty principle says that the shorter the time interval you are looking at, the larger the uncertainty in energy. Mathematically, the product of the uncertainty in energy and the uncertainty in time must be at least as large as Planck's constant divided by 4 pi. This might sound abstract, but it has a concrete and spectacular consequence. For very short time intervals, the uncertainty in energy can be large. So large, in fact, that the vacuum can temporarily contain enormous amounts of energy as long as this energy appears and disappears quickly enough. It is as if the universe has an accounting system that checks energy conservation, but it only checks periodically. Between checks, energy can fluctuate wildly as long as it balances out by the next check. These energy fluctuations manifest as particle-antiparticle pairs popping into existence out of the vacuum. An electron and a positron, a particle of matter and a particle of antimatter can spontaneously appear together, exist for a tiny fraction of a second, and then annihilate back into nothing. During their brief existence, they are real particles with real mass and real energy, borrowing that energy from the quantum uncertainty of the vacuum itself. These are called virtual particles, but this name is somewhat misleading. They are not imaginary or hypothetical. They have measurable physical effects. The reason they are called virtual is that they cannot travel far or exist for long. They are constrained by the uncertainty principle. A virtual particle pair with more energy can exist for less time, and during that time they can travel a shorter distance before they must annihilate. Let me give you a sense of the scales we're talking about. A virtual electron-positron pair might exist for about 1 part in 10 to the 21st of a second. During that time, even travelling at the speed of light, they could only move a distance of about 1 part in a trillion of a meter. These are unimaginably small scales, far smaller than an atom, far smaller than even a nucleus. But just because these scales are tiny does not mean virtual particles are irrelevant. In quantum field theory, which is the framework that combines quantum mechanics with special relativity, virtual particles are responsible for all of the forces between real particles. When 2 electrons repel each other, for instance, they do so by exchanging virtual photons, particles of light that pop into existence between them. Moreover, virtual particles have been detected indirectly through several experiments. The most famous is the Casimir effect, which we mentioned briefly before. Let me describe it in more detail because it beautifully demonstrates that virtual particles are real. Imagine you take 2 uncharged metal plates and place them parallel to each other in a vacuum separated by a tiny gap, less than a micrometer. According to classical physics, nothing should happen. There is no matter between the plates, no radiation, no forces. But when this experiment is actually performed, the plates are pushed together by a measurable force. Where does this force come from? The space between the plates and the space outside the plates are both filled with virtual particles, constantly appearing and disappearing. But here is the key point. Between the plates, only virtual particles with certain wavelengths can exist. They have to fit in the gap. Virtual particles come in all wavelengths, corresponding to all possible energies that the uncertainty principle allows, but the gap acts like a filter. Think of it like sound waves in an organ pipe. Only certain frequencies can resonate inside a pipe of a given length. Similarly, only virtual particles whose wavelengths are compatible with the gap size can exist between the plates. Outside the plates, there is no such restriction. All wavelengths of virtual particles can exist there. This creates an imbalance. There is more vacuum energy, more virtual particle activity outside the plates than between them. This difference in vacuum energy creates a net pressure that pushes the plates together. And this force has been measured in laboratories with exquisite precision. It matches the predictions of quantum theory exactly. Another consequence of virtual particles is what is called vacuum polarization. When you place an electrically charged particle in empty space, The virtual particles in the vacuum respond to that charge. Virtual electron-positron pairs appear near the charged particle, and they align themselves with the electric field. The positive virtual particles get pulled slightly closer to a negative charge, while the negative virtual particles get pushed away. This creates a subtle screening effect, slightly weakening the apparent charge of the particle. This effect has also been measured experimentally and agrees perfectly with theory. Now, here is something crucial to understand. In normal flat space-time, far from any gravitational fields, virtual particle pairs always annihilate each other. They appear together, exist briefly, and recombine. The net result is that on average, over long times and large distances, the vacuum contains no real particles. All you see is empty space, even though it is seething with virtual particle activity on microscopic scales. But what happens when space-time is not flat? What happens when there is extreme curvature, like near a black hole? This is where things get interesting, and this is exactly what Hawking started to investigate. In curved space-time, the geometry itself can affect the quantum vacuum. The curvature can interact with the virtual particles in unexpected ways. It can, under certain circumstances, pull a virtual particle pair apart before they have a chance to annihilate. And if the curvature is strong enough, if it changes rapidly enough over the distance that a virtual particle can travel, something remarkable can happen. One member of the pair can become a real particle, a particle that escapes and travels away, while its partner stays virtual or becomes real with negative energy. This transformation from virtual to real particles is not magic. Energy must still be conserved. If a particle becomes real and escapes with positive energy, that energy must come from somewhere. In flat space-time, there is nowhere for it to come from, so virtual pairs always annihilate. But in curved space-time, especially near a black hole, the energy can come from the gravitational field itself, from the curvature of space-time. This process is called particle creation from curved space-time, and it was understood in various contexts before Hawking's work. Physicists knew that the expanding universe could create particles from the vacuum, and that accelerating observers would see particles even in what a stationary observer sees as empty space. These were called the cosmological particle creation and the Unruh effect, respectively. What Hawking did was apply these ideas to the specific case of a black hole's event horizon. And what he found there was something nobody expected: a mechanism by which black holes could radiate, could lose energy, could have a real temperature and real entropy. The impenetrable prison that was the black hole was about to reveal its most surprising secret. Chapter 6. Hawking's Breakthrough Calculation. In 1974, Stephen Hawking published one of the most important papers in theoretical physics of the 20th century. The title was simply Black Hole Explosions, and in it he showed that black holes are not black after all. They emit radiation, they have a temperature, and they slowly evaporate over time. The discovery was so unexpected that Hawking himself initially thought he had made a mistake. Let us walk through the key insights step by step, building up the picture carefully so we can understand not just what Hawking discovered, but why it happens. Picture the event horizon of a black hole. Remember that this is not a physical surface, but rather a boundary in space-time, the point beyond which nothing can escape. Right at this boundary, space-time is extremely curved. The gravitational tidal forces are enormous, and most importantly, the geometry of space-time is changing rapidly as you move from just outside the horizon to just inside it. Now add quantum mechanics to this picture. The vacuum near the event horizon is filled with virtual particle-antiparticle pairs, just like everywhere else in the universe. These pairs are constantly appearing and disappearing. In flat space-time, far from the black hole, they simply annihilate and nothing interesting happens. But right at the horizon, something different can occur. When a virtual particle pair appears very close to the event horizon, the two particles are separated by a tiny distance, roughly the wavelength associated with their energy. But near the horizon, space-time curvature is so extreme that this tiny distance matters. One particle might be just outside the horizon while its partner is just inside. Here is where the magic happens. If one particle falls inside the horizon, it cannot come back out to annihilate with its partner. The pair is separated by the event horizon. The particle outside the horizon can escape to infinity. It becomes a real particle, no longer virtual, carrying real energy away from the black hole. But wait, you might ask. Where did the energy come from to make this virtual particle real? Energy cannot be created from nothing. This is where the truly clever part of Hawking's insight comes in. The particle that fell into the black hole carries negative energy from the perspective of the black hole. This sounds impossible at first. How can anything have negative energy? But remember, energy is always measured relative to something. Inside the event horizon, where all paths lead to the singularity, the geometry of space-time is so warped that particles can have what appears to us as negative energy relative to the outside universe. Think of it this way. The particle outside escapes with positive energy. To conserve total energy, the black hole must lose an equivalent amount of energy. The particle that fell in effectively removes energy from the black hole equal to the energy the escaping particle carries away. From the black hole's perspective, it has absorbed a negative energy particle, which is the same as losing energy. This means the black hole's mass decreases. Every time a particle escapes as Hawking radiation, the black hole gets slightly lighter. This was absolutely revolutionary. Before Hawking's calculation, black holes were thought to be eternal objects that could only grow, never shrink. They absorbed everything and emitted nothing. But quantum mechanics changes this picture completely. Hawking worked through the mathematics rigorously using quantum field theory in curved space-time. He calculated what an observer far from the black hole would see if they measured the quantum fields near the horizon. And what he found was astonishing. The spectrum of particles being emitted was exactly that of a perfect blackbody, a thermal radiator. Remember, we talked about blackbody radiation earlier, how any object with a temperature emits light and particles with a characteristic spectrum. A blackbody spectrum has a specific mathematical form, a curve that depends only on temperature. Hawking found that black holes emit radiation with precisely this spectrum. This meant that black holes genuinely have a temperature, not just something mathematically analogous to temperature, but a real physical temperature. The temperature of a black hole is inversely proportional to its mass. This is a crucial point. The formula is remarkably simple and beautiful. The temperature equals a constant involving Planck's constant, the speed of light, and the gravitational constant divided by the mass of the black hole. What this means is that bigger black holes are colder, while smaller black holes are hotter. Let us put some numbers on this to understand the scales involved. A black hole with the mass of our Sun would have a temperature of about 1/10,000,000th of a degree above absolute zero. That is incredibly cold, far colder than the cosmic microwave background radiation that fills the universe, which is about 3 degrees above absolute zero. So a solar mass black hole actually absorbs more radiation from its surroundings than it emits. It grows rather than shrinks, at least in our current universe. But consider a smaller black hole, one with the mass of a mountain, say 1,000,000,000,000 kilograms. This black hole would be about the size of a proton, and its temperature would be around 1,000,000,000,000 degrees. It would be glowing intensely, radiating particles at an enormous rate. And as it radiates and loses mass, it gets hotter still, creating a runaway process that ends in a violent explosion. The inverse relationship between mass and temperature is what makes black hole evaporation such a dramatic process. As the black hole loses mass, its temperature increases, which makes it radiate faster, which makes it lose mass even faster, which raises the temperature further. The process accelerates exponentially as the black hole shrinks. Hawking's calculation also revealed the mechanism behind Bekenstein's entropy formula. The entropy of a black hole is indeed proportional to the area of its event horizon. Specifically, the entropy equals 1/4 of the horizon area measured in units of the Planck length squared. The Planck length is the fundamental quantum scale, about 10 to the minus 35 meters, unimaginably tiny. This formula has profound implications. It means that a black hole can store an enormous amount of entropy. A solar mass black hole has an entropy of about 10 to the power of 60, a number with 60 zeros after it. For comparison, the Sun itself, as a hot ball of gas, has an entropy of about 10 to the 57. The black hole has 1,000 times more entropy, despite having the same mass. This tells us that black holes are the most efficient stores of entropy in the universe. They pack more disorder, more hidden information into a given volume than anything else. This makes sense in a way. All the information about everything that fell into the black hole must be encoded somewhere, and the entropy measures how many possible configurations could produce the same external appearance. Hawking presented his results at a conference in Oxford in February 1974. The audience was stunned. Many physicists simply did not believe it at first. The idea that black holes could radiate seemed to contradict everything they knew. Some thought Hawking must have made an error in his calculations. But as physicists checked and rechecked his work, using different methods and approaches, they all arrived at the same conclusion. Hawking was right. John Wheeler, who had been Bekenstein's advisor and was one of the pioneers of black hole physics, was convinced. He embraced the result enthusiastically. Bekenstein felt vindicated because his ideas about black hole entropy and temperature, which had been so controversial, turned out to be correct, though for reasons he had not fully anticipated. But Hawking himself was troubled by his own discovery. Yes, he had shown that black holes have temperature and entropy, resolving the thermodynamic paradox. But he had created a new and even deeper problem. If black holes evaporate completely, radiating away all their mass as thermal radiation, what happens to all the information about what fell in? The Hawking radiation is purely thermal, determined only by the temperature, which depends only on the mass. It seems to carry no information about what created the black hole or what fell into it. This appeared to be a direct violation of quantum mechanics. Information, according to quantum theory, cannot be destroyed. It can be scrambled, encoded in complex ways, spread across many particles, but it must always exist somewhere. Yet the evaporation of a black hole seemed to erase information permanently from the universe. Hawking had solved one paradox, only to create another, one that would become known as the black hole information paradox. This puzzle would occupy some of the greatest minds in physics for the next 50 years, and continues to be an active area of research today. But before we dive into that deep mystery, let us first understand what Hawking radiation means for the life and death of black holes. Chapter 7. The Temperature of Nothingness. Now that we understand how Hawking radiation works, let us explore what it means in practical terms. What would this radiation actually look like? What happens to black holes over time? And why do we not see this radiation pouring out of black holes everywhere in the universe? The key to answering these questions lies in understanding the temperature of black holes and how incredibly small that temperature is for astronomical black holes. Remember, the temperature is inversely proportional to mass. The more massive the black hole, the colder it is. Let us work through some specific examples to get a feeling for the numbers. The smallest black holes we know of in nature are stellar mass black holes formed from collapsed stars. These have masses of at least a few times the mass of our Sun. A black hole with exactly the Sun's mass would have a temperature of approximately 6/100ths of a microkelvin. That is 600,000ths of a millionth of a degree above absolute zero. To put this in perspective, the coldest natural place in the universe is not a black hole, but rather the voids of intergalactic space, far from any stars or galaxies. Even there, the cosmic microwave background radiation fills all of space with a temperature of about 2.7 degrees above absolute zero. This is the afterglow of the Big Bang, cooled by the expansion of the universe over nearly 14 billion years. A solar mass black hole at 6/100ths of a microkelvin is nearly 50 million times colder than the cosmic microwave background. This means that instead of radiating energy, such a black hole actually absorbs energy from the surrounding universe. It swallows the cosmic microwave background radiation faster than it emits Hawking radiation. Far from evaporating, black holes in our universe are actually growing due to this imbalance. Supermassive black holes, the kind found at the centers of galaxies, including our own Milky Way, are even colder. The black hole at the center of our galaxy has a mass about 4 million times that of the Sun. Its temperature is about 15 billionths of a microkelvin. The supermassive black hole at the center of the giant elliptical galaxy Messier 87, which was recently imaged by the Event Horizon telescope, has a mass of about 6.5 billion solar masses. Its temperature is a mere 7 trillionths of a microkelvin, almost incomprehensibly close to absolute zero. So why did Hawking call his paper black hole explosions, if real black holes are so cold they barely radiate at all? The reason is that small black holes behave very differently. Consider a hypothetical black hole with the mass of the Moon, roughly 1% of Earth's mass. Such a black hole would be about the size of a tennis ball, and would have a temperature of about 3 degrees above absolute zero, slightly warmer than the cosmic microwave background. This hypothetical black hole would be in rough equilibrium with the universe. It would radiate energy at almost the same rate as it absorbs energy from the cosmic background. Over time, as the universe expands and the cosmic microwave background cools, this black hole would eventually begin to evaporate, very slowly at first. Now let us go smaller. A black hole with the mass of Mount Everest, roughly 10 trillion kilograms, would be about the size of an atomic nucleus. Its temperature would be around 100 billion degrees, hotter than the core of any star. Such a black hole would radiate intensely, glowing with gamma rays and producing massive numbers of high-energy particles. But here is where things get truly dramatic. Because the temperature increases as the black hole shrinks, and higher temperature means faster radiation, the evaporation process accelerates. A black hole with the mass of Mount Everest would evaporate completely in about 1 billion years. That sounds like a long time, but it is much shorter than the current age of the universe. As this black hole shrinks, losing mass through radiation, it gets hotter and hotter. In its final second of existence, it would radiate more energy than a large star produces in an entire year. The very last moments would be an enormous explosion as the black hole completely evaporates in a flash of radiation and particles. Hence Hawking's title, Black Hole Explosions. Could such small black holes exist? They did not form from collapsing stars because stars cannot form black holes this small. The smallest black hole that can form from stellar collapse is several times the mass of the Sun. But in the early universe, in the first fraction of a second after the Big Bang, conditions were so extreme that tiny black holes might have formed from quantum fluctuations in the density of matter. These are called primordial black holes. If primordial black holes formed in the early universe, the ones with masses less than about 100 million tons would have evaporated by now, after roughly 14 billion years. Black holes with masses around 100 million tons would be reaching the explosive end of their evaporation right now. This is exciting because it means we might be able to detect these explosions as bursts of high-energy radiation and particles. Astronomers have searched for such bursts but have not definitively detected any yet. This tells us that if primordial black holes exist, they must be quite rare, or they must have formed with masses larger than this critical value. The search continues because detecting even one primordial black hole explosion would be revolutionary, providing direct evidence for both Hawking radiation and for these exotic remnants from the early universe. For larger black holes, the ones we know exist, the evaporation times are almost incomprehensibly long. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate completely. That is a 1 followed by 67 zeros, a number so large it is hard to grasp. For comparison, the current age of the universe is only about 10 to the 10th years, 14 billion years. A solar mass black hole would outlive the current universe by a factor of 10,000 trillion, 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 trillion. Supermassive black holes take even longer. The 4 million solar mass black hole at the center of our galaxy would take about 10 to the 87 years to evaporate. By the time it evaporated, the universe would be unrecognizable. All stars would have long since burned out. Protons themselves might have decayed. The universe would be a cold, dark, nearly empty place, with these black holes among the last remaining objects, slowly leaking energy into the void through Hawking radiation. But eventually, no matter how massive the black hole, it will evaporate. The process is inevitable. Quantum mechanics guarantees it. Every black hole will eventually return its energy to the universe, completing a cycle that began when matter fell in. This gives black holes a lifespan, a beginning and an end, rather than being eternal, unchanging objects. The spectrum of Hawking radiation also tells us something interesting. Remember that it is a thermal spectrum, like the radiation from a hot piece of metal or the glow from a fire. This spectrum contains particles of all types. Mostly, Hawking radiation consists of photons, particles of light. But there are also neutrinos, gravitons if they exist, and even occasionally heavier particles like electrons, positrons and quarks, though these are much rarer because they require more energy to create. The typical energy of particles in the radiation is proportional to the temperature. For a solar mass black hole with its incredibly low temperature, the typical photon in the Hawking radiation would have an energy corresponding to a wavelength larger than the observable universe. Such photons would be essentially impossible to detect because their wavelength is bigger than the detectors, bigger than planets, bigger than galaxies, bigger than anything we could possibly build. Only for very small hot black holes does the Hawking radiation become energetic enough to detect. A black hole with the mass of Mount Everest radiates primarily in gamma rays, the highest energy form of light. These gamma rays would have energies millions of times higher than visible light, exactly the kind of radiation we could potentially detect with gamma-ray telescopes if such a black hole were nearby. This raises an interesting question about the nature of the radiation. Is Hawking radiation truly radiation coming out of the black hole, or is it really coming from the vacuum just outside the black hole? This question is subtle and has been the subject of much debate among physicists. The answer depends on how you look at it. From one perspective, the radiation originates from the vacuum just outside the event horizon, from the separation of virtual particle pairs, as we described. In this view, nothing actually comes out from inside the black hole. The horizon itself never emits anything. Instead, the quantum vacuum near the horizon produces real particles that escape. From another perspective, you can trace the particles in the Hawking radiation backward in time using quantum field theory. When you do this carefully, you find that their quantum histories extend into the black hole's past, to the time before the horizon formed. In this view, the radiation does carry information from inside the black hole, encoded in quantum correlations. These two perspectives are both correct, but emphasize different aspects of the same quantum process. This ambiguity about exactly where the radiation comes from turns out to be closely related to the information paradox. If the radiation comes purely from the vacuum outside, it cannot carry information about what fell in. But if it somehow originates from inside, then maybe information can escape after all. Chapter 8. The evaporation process. Let us now follow the complete life cycle of a black hole, from formation to evaporation, painting a picture of what actually happens over its lifetime. This journey will take us through timescales that dwarf the current age of the universe, but it is a journey that quantum mechanics tells us must eventually complete. Imagine a massive star, much larger than our Sun, perhaps 20 or 30 solar masses. This star burns brightly for millions of years, fusing hydrogen into helium in its core, then helium into carbon and oxygen, then heavier and heavier elements. Each stage of fusion produces the energy that holds the star up against its own gravity. But fusion cannot continue forever because iron will not fuse and release energy. When the core becomes iron, the star's fate is sealed. Without energy from fusion, the core can no longer support itself. In less than a second, it collapses catastrophically. The outer layers fall inward at tremendous speed, rebound off the collapsing core, and explode outward in a supernova, one of the most violent events in the universe. Meanwhile, the core continues collapsing. If it is massive enough, no force can stop it. Neutron degeneracy pressure, which holds up neutron stars, fails. The core collapses past its Schwarzschild radius and a black hole forms. At the moment of formation, the new black hole has roughly the mass of the original stellar core, perhaps 3 to 10 times the mass of the Sun. Its event horizon has a radius of roughly 10 to 30 kilometers. Its temperature, according to Hawking's formula, is around 10 microkelvins to 3 microkelvins, cold beyond imagination. The black hole settles down quickly through a process called ringdown. Any irregularities in its shape vibrate away as gravitational waves, ripples in space-time itself. Within a fraction of a second, the black hole becomes perfectly smooth and symmetric, characterized only by its mass and rotation. It has become the simplest macroscopic object in the universe, with no features, no details, no structure beyond those two numbers. Now begins the long wait. The black hole sits in space, occasionally accreting matter that falls nearby, gradually growing. If it is in a binary system with another star, it might pull gas from its companion, creating an accretion disk of superheated material spiraling inward. This matter heats up to millions of degrees as it falls, emitting intense X-rays that we can detect with space telescopes. This is how we discover most stellar mass black holes, by the radiation from matter falling in, not from Hawking radiation coming out. The Hawking radiation during this phase is completely negligible. The black hole radiates with a power of only about 10 to the minus 30 watts, less than a trillionth of the power of a single flashlight. Meanwhile, it absorbs the cosmic microwave background radiation at a much higher rate, about 10 watts. The black hole grows rather than shrinks, taking in far more energy than it releases. This situation continues for an enormously long time. Stars eventually burn out. The Sun will become a white dwarf in about 5 billion years. Much later, in perhaps 10 trillion years, the last stars in the universe will fade and die. The universe will enter what is called the degenerate era, where the only significant objects are white dwarfs, neutron stars, and black holes, along with whatever planets and asteroids remain. Even in this dark era, our black hole continues absorbing more than it emits because the cosmic microwave background, though cooler than today, still has a higher temperature than the black hole. But the universe keeps expanding, and as it expands, the cosmic microwave background keeps cooling. Eventually, perhaps after 10 to the 40 years, a billion years, the cosmic microwave background will have cooled to below the black hole's temperature. At this point, finally, the black hole begins to evaporate in earnest. It is now radiating more energy than it absorbs from its surroundings. The process is still incredibly slow at first. The power radiated is tiny, and the black hole's mass decreases imperceptibly. But remember, as the mass decreases, the temperature increases, and the rate of radiation increases as well. For a black hole with an initial mass of 5 times the Sun, the evaporation takes approximately 10 to the 67 years. Let us try to comprehend this number. If you wrote out this number in normal notation, it would have 67 digits. If you counted 1 year per second, it would take you more than a trillion times the current age of the universe just to count to 10 to the 30. You would not even be a tiny fraction of the way to 10 to the 67. During most of this time, the black hole shrinks so slowly that its radius barely changes. But in the last stages, the process accelerates dramatically. When the black hole has shrunk to planetary mass, roughly the mass of Earth, its temperature has risen to about 1/1000th of a degree. It is still incredibly cold, but warming up. The black hole's radius is now about 9 millimeters, the size of a marble. The evaporation continues, faster and faster. When the mass reaches that of Mount Everest, the temperature is 100 billion degrees. The black hole is now about the size of a proton, radiating intensely in gamma rays. From this point, it takes only about 1 billion years to evaporate completely, less time than the current age of the solar system. In the final million years, the black hole has shrunk to the mass of a large asteroid. Its temperature is now millions of degrees, and it glows brilliantly in X-rays and gamma rays. Anyone nearby, if there were anyone left in this incredibly distant future, would see a brilliant point of light, a tiny star blazing with the intensity of a nuclear explosion. The final 1,000 years are spectacular. The black hole now has the mass of a mountain, temperature measured in trillions of degrees, radiating with a power equal to a large star. The event horizon has shrunk to the size of an atom. Quantum effects become overwhelming. The smooth predictions of classical general relativity break down completely. In the final second, the black hole has the mass of a small spacecraft, perhaps 100 tons. The temperature is beyond comprehension, quadrillions of degrees. The black hole releases as much energy in this final second as a large star produces in a year. The event horizon is now comparable in size to the Planck length, the smallest meaningful distance scale in physics. And then, in a flash, it is gone. The black hole completely evaporates in a final burst of radiation. What exactly happens in this final moment is uncertain because we do not have a complete theory of quantum gravity. The energy of individual quanta becomes comparable to the total mass energy of the black hole. Space-time itself becomes quantum mechanical, fluctuating wildly. Perhaps a tiny remnant is left behind, a Planck mass nugget of exotic matter. Perhaps the black hole simply vanishes completely, its mass converted entirely into radiation. This final explosion releases an enormous amount of energy in a tiny volume. If it happens in empty space, the radiation simply spreads out and dissipates. But the burst would be spectacular, containing high-energy gamma rays, showers of particles and antiparticles, neutrinos, and possibly even exotic particles we have never detected. For a brief instant, conditions near the evaporating black hole resemble the very early universe just after the Big Bang. After the explosion, nothing remains except the radiation spreading outward through space. The black hole has returned all its mass to the universe in the form of energy. The matter and information that fell into the black hole billions of years ago has seemingly vanished, converted into this featureless thermal radiation. Or has it? This question brings us to perhaps the deepest mystery in all of theoretical physics. Chapter 9. Why this matters. The information paradox deepens. Hawking's discovery of black hole radiation solved one problem but created another that is arguably even more troubling. The question is simple to state but incredibly difficult to answer. What happens to information that falls into a black hole? To understand why this is such a profound question, we need to think carefully about what physicists mean by information. In everyday language, information means facts, data, knowledge. But in physics, information has a much more specific meaning. It refers to the complete quantum state of a system, all the properties and quantum numbers that fully specify what that system is. Let us start with a simple example. Suppose you have a single electron. To completely describe this electron, you need to specify several things. You need to know its position, though quantum mechanics only allows you to specify this probabilistically. You need to know its momentum. You need to know its spin, whether it is spinning up or spinning down. You also need to know its quantum phase, a subtle property that affects how it interferes with other quantum particles. Now imagine you have not one electron, but a billion electrons arranged in a complex system like the atoms in your body. The information content of this system is enormous. You would need to specify the quantum state of every single electron, every proton, every neutron, all their positions, momenta, spins, and phases. This is an unimaginable amount of information, but in principle it exists and fully describes the system. Quantum mechanics makes a fundamental statement about this information. It says that information is conserved in any physical process. This is embedded in the mathematical structure of quantum theory through what is called unitarity. When a quantum system evolves from one state to another, the transformation is unitary, meaning it is reversible. If you know the final state precisely, you can work backward and determine the initial state. No information is lost. This conservation of information has been tested countless times in particle physics experiments, in atomic physics, in quantum optics, in every domain where quantum mechanics applies. It has never been violated. It is as solid a principle as energy conservation or momentum conservation. But now consider what happens when you throw something into a black hole. Let us throw in that complex system of a billion electrons we mentioned. From outside the black hole, we watch the object fall toward the event horizon, getting more and more redshifted, appearing to slow down and freeze just above the horizon. Eventually, the light from it becomes so redshifted that we can no longer detect it. The object has effectively disappeared from our universe. The black hole's mass increases by the mass of the object we threw in. Its event horizon grows slightly to accommodate the added mass. But here is the problem. From outside, we can measure only three properties of the black hole: its mass, its electric charge, if it has any, and its angular momentum, if it is rotating. Three numbers. That is all we can know about the black hole from outside observations. Those three numbers cannot possibly encode all the information about the billion electrons we threw in. That information described an enormously complex quantum state with countless details. But the black hole has swallowed all that complexity and presents us with just three numbers. Where did all that information go? You might think the information is simply hidden inside the black hole, beyond the event horizon where we cannot observe it. This would be fine if the information stayed there forever. But Hawking radiation changes everything. The black hole evaporates. Given enough time, it will completely disappear. And according to Hawking's calculation, the radiation it produces depends only on the black hole's temperature, which depends only on its mass at any given moment. Thermal radiation, by its very nature, is featureless. It is characterized by a temperature and nothing else. If you measure thermal radiation from a hot piece of metal, you can determine the temperature of the metal, but you cannot tell whether the metal is iron or copper or steel. The radiation is the same for any material at the same temperature. Similarly, Hawking radiation depends only on the mass of the black hole, not on what created it or what fell into it. This means that two different black holes with the same mass but formed from completely different things, one from collapsed stars and one from compressed gas, would radiate in exactly the same way. They would be indistinguishable from outside. When they evaporate completely, they would both leave behind the same featureless radiation. All information about what they were made from appears to be lost. This is the information paradox. If information is truly lost when black holes evaporate, then quantum mechanics is wrong about information conservation. The evolution of the universe is not unitary. You cannot work backward from the final state, the Hawking radiation, to determine the initial state, what fell into the black hole. Information has been destroyed. Many physicists found this conclusion unacceptable. Quantum mechanics is too successful, too well tested to abandon. There must be another explanation. Perhaps the information is not lost, but is somehow encoded in the Hawking radiation in a very subtle way that the original calculation missed. Perhaps information escapes through quantum correlations between particles that are too complex to see in the semi-classical approximation Hawking used. Or perhaps something more radical is needed. Maybe information is encoded on the event horizon itself, or maybe it escapes through quantum tunneling, or maybe black holes leave behind remnants that store the information. Or maybe the entire picture of space-time breaks down at the singularity and information is preserved in a way we do not yet understand. Hawking himself initially believed that information was genuinely lost, that quantum mechanics needed to be modified. This was a bold stance because it went against one of the deepest principles of quantum theory. In 1976, Hawking published a paper arguing that black hole evaporation is fundamentally non-unitary, that it genuinely destroys information. This sparked intense debates that continued for decades. The paradox has profound implications beyond black holes. If information can be destroyed anywhere, then physics loses its predictive power. If you cannot work backward from effects to causes, if the past does not determine the future uniquely, then science itself is undermined. Everything we know about the universe comes from observing outcomes and inferring the processes that cause them. If information can be destroyed, this entire approach fails. Moreover, the paradox touches on the nature of quantum mechanics and gravity. Hawking's calculation used quantum field theory in a fixed classical space-time. It treated the quantum fields as fluctuating, but treated gravity and space-time as smooth and deterministic. Perhaps this is not good enough. Perhaps to really understand what happens to information, we need a full theory of quantum gravity, where space-time itself is quantum mechanical. The search for this theory has been one of the driving forces in theoretical physics for the past 50 years. String theory, loop quantum gravity and other approaches all attempt to quantize space-time and unify quantum mechanics with general relativity. The black hole information paradox serves as a crucial test case. any proposed theory of quantum gravity must explain what happens to information in black holes. If it cannot solve this puzzle, it cannot be the correct theory. The paradox also raises questions about the nature of space-time and the holographic principle. If all the information that falls into a black hole is somehow encoded on the two-dimensional surface of the event horizon, as the entropy formula suggests, then perhaps this is a general feature of space-time. Perhaps all the information in any region of space is actually encoded on its boundary, like a hologram where a two-dimensional surface contains a three-dimensional image. This holographic principle, if correct, would represent a fundamental shift in how we understand reality. It would mean that space-time is not fundamental but emergent, that the three dimensions we experience are somehow projections of information encoded on lower dimensional surfaces. This is now an active area of research, with connections to quantum entanglement, quantum error correction, and the fundamental nature of gravity. For years, the paradox remained unsolved. Some of the greatest minds in physics wrestled with it. Hawking, who had created the paradox with his discovery, worked on it for the rest of his life. He eventually changed his mind and came to believe that information is preserved, though the mechanism remained unclear. In 2004, he famously conceded a bet he had made with fellow physicist John Preskill about the fate of information in black holes. Today, the consensus among most physicists is that information must be preserved, but exactly how it is preserved remains controversial. Recent developments using tools from quantum information theory and string theory suggest that information does escape in the Hawking radiation, but in a highly scrambled form that requires incredibly precise measurements to decode. The radiation is not exactly thermal, but contains subtle correlations that encode the information about what fell in. But this creates new puzzles. If information escapes in the radiation, then it must somehow make its way from inside the event horizon to outside. Yet, by definition, nothing can travel outward from inside the horizon. This leads to ideas like black hole complementarity, where different observers have fundamentally different but equally valid descriptions of what happens, or firewalls, where the event horizon might be a lethal barrier of high-energy particles rather than the smooth surface general relativity predicts. The information paradox thus remains at the frontier of physics, driving research and challenging our deepest assumptions about the nature of reality, information, space-time, and quantum mechanics. It is a testament to the power of Hawking's discovery that half a century later we are still working to understand its full implications. Chapter 10. Attempts to resolve the paradox. Over the past 50 years, physicists have proposed numerous creative solutions to the information paradox. Each solution offers insights, but also faces challenges. Let us explore the major proposals and see how our understanding has evolved, even if we have not yet reached a final answer. The first major approach is to look for subtle information in the Hawking radiation itself. Perhaps the radiation is not exactly thermal, but contains tiny deviations that encode information about what fell into the black hole. This information might be hidden in quantum correlations between the emitted particles, correlations so subtle that they do not affect the overall thermal spectrum, but are there if you look carefully enough. To understand this idea, imagine scrambling an egg. The scrambled egg looks completely different from the original egg with its separate white and yolk. The information about the original state seems to be lost in the chaos of scrambling. But in principle, if you could track every single molecule, every atomic motion during the scrambling process, you could work backward and reconstruct the original state. The information is not lost, just enormously scrambled and difficult to access. Similarly, the Hawking radiation might appear thermal when you look at individual particles or simple measurements. But if you could perform incredibly detailed measurements of many particles and their quantum correlations, you might be able to extract the information about what fell in. The radiation would be like a highly encrypted message. Without the key, the quantum correlations, it looks like random noise. With the key, you can decode the information. This approach faces a significant challenge. For the information to escape, it must somehow get from inside the event horizon to outside. But general relativity forbids any signal from traveling outward across the horizon. How can information escape without something carrying it outward? One proposed answer involves quantum entanglement, the strange connection between quantum particles that Einstein called spooky action at a distance. When a particle pair is created at the horizon, with one falling in and one escaping, they are entangled. They share a quantum connection even though they are separated. Perhaps information can be transferred through this entanglement without any signal traveling across the horizon. This leads to the second major approach, black hole complementarity. This idea, proposed by Leonard Susskind, Gerard 't Hooft and others, suggests that different observers have fundamentally different but equally valid descriptions of what happens at a black hole. An observer falling into the black hole sees the information cross the horizon and move toward the singularity. An observer far outside sees the information somehow encoded on or near the horizon and eventually released in the Hawking radiation. Both descriptions are correct from their respective viewpoints. Just as in special relativity, different observers can disagree about whether two events are simultaneous and both be right. The key point is that no single observer can verify both descriptions simultaneously because you cannot both fall into the black hole and remain outside to see the radiation. The two perspectives are complementary, meaning they apply to non-overlapping sets of observations. This is a radical idea. It suggests that there is no single observer-independent description of what happens at a black hole. Physical reality itself depends on perspective in a way that goes beyond what we see in normal relativity. For the outside observer, information never really enters the black hole. It gets stuck near the horizon, scrambled, and eventually re-emitted. For the infalling observer, information smoothly crosses the horizon and moves toward the singularity. Both stories are true in their own domains. Black hole complementarity resolves the paradox by denying that there is a paradox. Information does not get lost because from the outside perspective it never entered the black hole in the first place. It was always on the horizon, always accessible, just highly scrambled. The infalling observer sees something different, but that observer cannot communicate their observations back to the outside once they cross the horizon, so there is no contradiction. However, this solution faces its own deep challenge, which emerged around 2012 and became known as the firewall paradox. The problem arises when you think carefully about the quantum entanglement of the Hawking radiation. For information to escape in the radiation, particles emitted late in the black hole's life must be entangled with particles emitted much earlier. This is necessary to carry the information about what fell in. But here is the rub. Each outgoing Hawking radiation particle is created from a virtual pair at the horizon. Standard quantum field theory in curved space-time says that the outgoing particle should be entangled with its partner that fell into the black hole. This entanglement is crucial for the derivation of Hawking radiation in the first place. It is what makes the radiation thermal. The problem is that a quantum particle cannot be maximally entangled with two different systems at once. This is a fundamental principle of quantum mechanics. So, the late-time radiation particle cannot be entangled both with its partner inside the black hole and with the early radiation that escaped long ago. Something has to give. If you insist that the late radiation is entangled with the early radiation to preserve information, then it cannot be entangled with its partner inside the black hole. But if the pair at the horizon is not entangled, then quantum field theory predicts something shocking. The horizon becomes a firewall, a region of incredibly high energy density that would incinerate anything trying to cross it. This contradicts general relativity, which says the horizon should be a perfectly smooth, non-threatening place for an infalling observer. So we are stuck between three principles that seem incompatible. We have unitarity, the requirement that information is conserved in quantum mechanics. We have the equivalence principle from general relativity, which says that free fall is indistinguishable from floating in empty space, so the horizon should be smooth. And we have locality, the principle that physics in one region should not depend on what is happening in distant regions. The firewall paradox suggests you can only keep two of these three principles. Giving up any one of them is deeply troubling. This has led to a flurry of research exploring which principle might need to be modified and how. Some physicists propose that the equivalence principle breaks down at the horizon, that general relativity is not exactly correct in this extreme situation. Others suggest that locality needs to be revised. The distant parts of space-time are more intimately connected than we thought, perhaps through quantum entanglement. Still others argue that we are not correctly accounting for the interior of the black hole in our calculations, and that a proper quantum gravity treatment would resolve the paradox. A third major approach to the information paradox involves the holographic principle. This principle emerged from studying the entropy of black holes and has grown into one of the most important ideas in modern theoretical physics. The key observation is that the entropy of a black hole is proportional to the area of its event horizon, not the volume it contains. This is very unusual. Normally, the amount of information or entropy in a system is proportional to its volume. A box twice as large can hold twice as many gas molecules and thus has twice as much entropy. But for black holes, entropy scales with area. It is as if all the information about what is inside the black hole is somehow encoded on its two-dimensional surface, like a hologram that contains three-dimensional information. This led physicists to wonder whether this is a general feature of space-time. Perhaps the information content of any region of space is actually encoded on its boundary. Perhaps the three-dimensional space we experience is somehow an illusion, a projection from information stored on a two-dimensional surface. This is the holographic principle proposed by Gerard 't Hooft and Leonard Susskind in the 1990s. The holographic principle received spectacular confirmation from string theory through what is called the ADS-CFT correspondence. This is a mathematical duality discovered by Juan Maldacena in 1997. It shows that a quantum gravity theory in a certain type of space-time, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the boundary of that space-time. Gravity in the bulk emerges from quantum entanglement in the boundary theory. This correspondence has been studied intensely and has passed countless consistency checks. It provides a concrete example where the holographic principle is realized exactly. Within this framework, black hole evaporation can be studied using the boundary theory, which is unitary and conserves information by construction. The information paradox is resolved because the entire process, including black hole formation and evaporation, is described by the unitary boundary theory. From this perspective, information is clearly preserved. However, translating this resolution back to our universe is challenging because our universe is not anti-de Sitter space. It is approximately flat, or perhaps slightly positively curved, not negatively curved like anti-de Sitter space. Whether similar holographic descriptions apply to realistic black holes in our universe remains an active area of research. A fourth approach involves quantum error correction and the idea that space-time itself might be built from quantum entanglement. Recent work has shown deep connections between the structure of space-time in holographic theories and quantum error-correcting codes, the mathematical structures that protect quantum information from noise and decohesion. In this picture, the smooth geometry of space-time emerges from a highly entangled quantum state. When information falls into a black hole, it gets encoded in a special way across the quantum state, similar to how quantum error-correcting codes distribute information across many qubits so that losing any small subset does not destroy the information. The Hawking radiation then represents a process where this encoded information is gradually recovered, though in a highly scrambled form. This approach suggests that information is never truly lost because it is protected by the quantum structure that gives rise to space-time itself. The information appears to be lost only if you treat space-time as classical and fixed. But once you account for the quantum nature of gravity, the preservation of information becomes manifest. Yet another proposal is that black holes do not evaporate completely, but leave behind remnants, small objects with a Planck mass that contain all the information about what fell in. These remnants would be incredibly small, about 10 to the minus 35 meters, but would have an enormous internal entropy, encoding the information of the much larger black hole that evaporated away. This idea is controversial because it seems to require an infinite number of internal states for the remnant, one for each possible configuration of the original black hole. This leads to various theoretical problems, including the possibility that virtual black holes and their remnants would dominate vacuum fluctuations and cause catastrophic instabilities. Most physicists are skeptical of remnants for these reasons, though the idea has not been definitively ruled out. Stephen Hawking himself proposed various ideas over the years. Initially, he believed information was truly lost and that quantum mechanics needed to be modified to account for this. Later, influenced by the holographic principle and AD-yes CFT correspondence, he changed his mind. In 2004, he conceded his famous bet with John Preskill, presenting an argument that information escapes through topological fluctuations in the event horizon. His argument was not widely accepted in its details, but it showed his acknowledgement that information probably is preserved after all. In 2016, shortly before his death, Hawking proposed yet another idea with Malcolm Perry and Andrew Strominger. They suggested that information is stored in soft hair on the black hole, meaning zero-energy gravitational or electromagnetic excitations at the horizon. These soft modes can carry information without affecting the mass or other macroscopic properties of the black hole. Whether soft hair can store enough information to resolve the paradox remains debated. The current consensus among most physicists is that information is somehow preserved, likely through subtle quantum correlations in the Hawking radiation that require a full quantum gravity theory to properly understand. The radiation is not exactly thermal, but contains minute deviations that encode the information, deviations that become important once the black hole has radiated away about half its original mass. The question of exactly how the information escapes and what an observer falling into an old, evaporating black hole would experience remains open. Is there a firewall? Does complementarity hold? Is space-time fundamentally holographic? These questions connect to the deepest issues in theoretical physics and will likely require new insights about the nature of quantum gravity to fully answer. What is clear is that Hawking radiation has transformed our understanding of black holes from simple classical objects into quantum systems with temperature, entropy, and information content. The paradoxes that arose from this discovery have driven much of theoretical physics over the past 50 years and continue to inspire new ideas about space-time, quantum mechanics, and the fundamental nature of reality. Chapter 11. What Hawking radiation reveals about the universe. Let us now step back from the technical puzzles and appreciate the broader picture. What does Hawking radiation tell us about the universe? What deep truths does it reveal about the nature of reality? The implications extend far beyond black holes themselves and touch on the most fundamental questions we can ask about existence. First and foremost, Hawking radiation shows us that quantum mechanics and gravity are deeply intertwined. Before Hawking's discovery, physicists could mostly study quantum mechanics and general relativity separately. Quantum mechanics governed the atomic and subatomic world. General relativity governed planets, stars, and galaxies. The two realms rarely overlapped, and when they did, you could usually treat one as a small correction to the other. Hawking radiation is different. It is a genuinely quantum gravitational effect that cannot be understood using either theory alone. You need quantum field theory to get the virtual particles and the concept of vacuum fluctuations. You need general relativity to get the event horizon and the curved space-time that separates the particle pairs. Neither theory by itself predicts the effect. It emerges only from their combination. This makes Hawking radiation one of our few windows into quantum gravity, the elusive theory that unifies quantum mechanics and general relativity. Even though we cannot detect Hawking radiation from real black holes because they are too cold, the fact that the effect exists in theory tells us something profound about how quantum mechanics and gravity must work together. The effect shows us that the vacuum of space is not a passive stage where events happen, but an active player in physics. The quantum vacuum has structure, energy, and dynamics. Near regions of extreme space-time curvature, this vacuum structure reveals itself through particle creation. This was known before Hawking in other contexts, such as the expansion of the universe creating particles from the vacuum, but Hawking radiation made it impossible to ignore. Second, Hawking radiation reveals that black holes are thermodynamic systems. They have temperature, they have entropy, they exchange energy with their environment through radiation. This means they are subject to the laws of thermodynamics, just like any other physical system. The second law of thermodynamics applies to black holes. The total entropy of the universe, including the entropy of black holes, always increases. This connection between black holes and thermodynamics is profound because it suggests that thermodynamic concepts like entropy and temperature are even more fundamental than we thought. They apply not just to matter and radiation, but to space-time itself. A black hole is not made of atoms or particles in the conventional sense. Its mass is compressed into a singularity, and what we observe from outside is pure curved geometry. Yet this geometry has a temperature and entropy. This suggests that thermodynamics might be more fundamental than either quantum mechanics or general relativity, that both of these theories are approximations to some deeper statistical description of reality. Many modern approaches to quantum gravity take this idea seriously, trying to understand space-time as an emergent phenomenon arising from some more fundamental microscopic degrees of freedom, just as temperature emerges from the motion of molecules. The formula for black hole entropy, proportional to the horizon area divided by 4 times the Planck area, is one of the most important equations in theoretical physics. It connects 3 fundamental constants: the gravitational constant from general relativity, Planck's constant from quantum mechanics, and Boltzmann's constant from thermodynamics. Any complete theory of quantum gravity must reproduce this formula, making it a powerful constraint on theoretical speculation. Third, Hawking radiation shows us that black holes are not eternal. They have a life cycle. They are born in gravitational collapse, or perhaps in the violent early moments of the Big Bang. They grow by accreting matter and merging with other black holes. Eventually they begin to evaporate, slowly at first, then faster and faster, until they disappear in a final burst of energy. They are not permanent features of the universe, but temporary structures that eventually return their mass energy to space. This gives us a picture of the very long-term future of the universe. In the far future, after all stars have burned out, after all matter has either fallen into black holes or been ejected into intergalactic space, after even the longest-lived stars and galaxies have faded, black holes will be the dominant objects. They will sit in an increasingly empty and cold universe, slowly evaporating through Hawking radiation. As each black hole evaporates, it will contribute a tiny amount of heat and light to the universe. Over unimaginable spans of time, all black holes will evaporate. The universe will be left with a thin gas of radiation and perhaps some remaining electrons and positrons, the lightest charged particles. This is sometimes called the black hole era of the universe, lasting from perhaps 10 to the 40 years to 10 to the 100 years after the Big Bang. After the black holes are gone, the universe enters what is called the dark era, where photons continue to redshift as space expands, and the universe becomes ever more dilute and cold, approaching but never quite reaching absolute zero. Whether the universe truly ends this way depends on other physics we do not fully understand, such as the nature of dark energy and whether protons decay. But Hawking radiation will certainly play a role in the universe's ultimate fate. Fourth, Hawking radiation reveals deep connections between information, entropy, and gravity. The information paradox shows us that information is not just a human concept related to knowledge or data. It is a physical quantity as fundamental as energy or charge. The universe keeps track of information at the quantum level, and this bookkeeping constrains what can happen in physical processes. The fact that black holes have entropy proportional to their horizon area suggests that information is somehow encoded geometrically. This leads to the holographic principle, the idea that information in a volume of space is bounded by the area of the surface enclosing it. If correct, this is a radical departure from our intuition. It means that the three-dimensional world we experience might be a kind of projection, that the fundamental degrees of freedom describing reality might live on lower dimensional surfaces. The holographic principle has profound implications for our understanding of space itself. It suggests that space is not fundamental, but emergent, built from something more basic. Just as temperature emerges from molecular motion and pressure emerges from molecular collisions, perhaps space emerges from quantum entanglement or some other microscopic structure we have yet to fully characterize. Fifth, Hawking radiation shows us that even the strongest gravity cannot completely trap information. The event horizon, that ultimate barrier beyond which nothing can escape classically, is not the final word. Quantum mechanics finds a way, through virtual particles and vacuum fluctuations, to extract information and energy from black holes. Nature is more subtle and more interconnected than classical physics suggests. This has implications for our understanding of causality and determinism. In classical general relativity, the future is completely determined by the past, and event horizons create regions that are causally disconnected from the outside universe. Hawking radiation shows that quantum mechanics softens these absolutes. Information that seemed trapped forever can eventually escape. Regions that seemed forever separated can influence each other through quantum effects. Sixth, Hawking radiation connects to the arrow of time, the mystery of why time flows in one direction. Entropy increases with time according to the second law of thermodynamics. This is why we remember the past but not the future, why eggs scramble but do not unscramble, why coffee cools down but does not heat up. The arrow of time points in the direction of increasing entropy. Black holes are the ultimate entropy increase. When organized matter with relatively low entropy falls into a black hole, it becomes part of the black hole's entropy, which is enormous. A black hole is the highest entropy state available for a given amount of mass. This makes black holes important for understanding the thermodynamic arrow of time. They represent the natural end state of gravitational systems left to evolve for long periods. Hawking radiation complicates this picture in interesting ways. As black holes evaporate, their entropy decreases because a smaller black hole has less horizon area and thus less entropy. But the entropy of the radiation they emit more than compensates, so total entropy still increases. The black hole plus radiation system has higher entropy than the black hole alone. This is consistent with the second law, but it shows that entropy can shift between different systems in subtle ways while always increasing overall. Seventh, Hawking radiation has inspired new mathematical tools and concepts that have applications far beyond black holes. The techniques Hawking developed for calculating quantum field theory in curved space-time have been applied to cosmology, to particle physics in accelerators, to condensed matter physics, and to many other areas. The concept of horizons creating temperature has been generalized to other contexts. For example, accelerating observers in empty space experience a temperature and see particles, even though inertial observers see only vacuum. This is called the Unruh effect, and while incredibly small for any achievable acceleration, it is a real prediction of quantum field theory that is closely related to Hawking radiation. The mathematics is nearly identical, showing that horizons and acceleration are intimately connected in creating thermal effects from the quantum vacuum. Researchers have even created analog systems in laboratories that mimic some aspects of Hawking radiation. Using fluids flowing faster than the speed of sound in the fluid, they create acoustic horizons, regions where sound waves cannot escape. These acoustic black holes exhibit a phenomenon similar to Hawking radiation, where phonons, quantized sound waves, are created at the horizon. While not exactly the same as gravitational black hole evaporation, These experiments demonstrate the robustness of the underlying quantum physics. Eighth, Hawking radiation reminds us of the limits of our knowledge and the mysteries that remain. Despite 50 years of intensive research, we still do not have complete answers to the questions it raises. We do not know precisely how information escapes from black holes. We do not know what happens at the singularity. We do not know whether firewalls exist at old black hole horizons. We do not have a complete theory of quantum gravity that can definitively resolve these issues. These open questions are not failures but opportunities. They mark the frontier of human knowledge, the boundary between what we understand and what remains to be discovered. They inspire new generations of physicists to push deeper, to develop new mathematical tools, to imagine new ways of thinking about space, time, matter, and information. The fact that such basic questions remain unanswered nearly a century after quantum mechanics and a century after general relativity shows how difficult it is to unite these two pillars of modern physics. Finally, Hawking radiation teaches us about the unity of physics. It connects quantum mechanics, general relativity, thermodynamics, and information theory. It shows that concepts we developed in one domain, like entropy and steam engines, apply to the most exotic objects in the universe. It demonstrates that nature is consistent, that the same underlying principles govern everything from atoms to galaxies, from virtual particles to cosmic horizons. This unity is both humbling and inspiring. It is humbling because it shows how much we still have to learn, how the universe continues to surprise us with unexpected connections and subtle effects. It is inspiring because it suggests that despite the apparent complexity of the world, there are deep, simple principles underneath, waiting to be discovered. Every mystery we solve reveals new mysteries, but each step forward brings us closer to understanding the fundamental nature of reality. Chapter 12. The Future of the Quest. As we conclude our journey through Hawking radiation and its implications, let us look forward. Where is the field heading? What questions remain open? What new discoveries might await us? The quest to understand black holes, quantum gravity, and the nature of space-time continues with ever-increasing sophistication and creativity. One of the most exciting frontiers is the direct detection of Hawking radiation. As we have discussed, the Hawking radiation from astronomical black holes is far too faint to detect. A solar mass black hole radiates with a power of only 10 to the minus 30 watts, billions of times less than the power received from the faintest stars visible to the largest telescopes. The radiation is also at incredibly long wavelengths, far into the radio spectrum and beyond, making it even harder to distinguish from background noise. However, there is a potential way to detect Hawking radiation from primordial black holes, tiny black holes that might have formed in the early universe. The Big Bang was an incredibly hot, dense, violent event. In the first fraction of a second, quantum fluctuations in the density of matter and energy were enormous. Some regions were much denser than average, and if these density fluctuations were strong enough, they could have collapsed directly into black holes. These primordial black holes would have a range of masses depending on when they formed and how large the fluctuations were. The interesting ones for Hawking radiation are those with masses around 100 million to 1 billion tons. Such black holes would be smaller than an atom, but would have temperatures of billions of degrees. They would have been evaporating since the Big Bang, and if any formed with just the right mass, they would be exploding right now, after 14 billion years of evaporation. The final explosion of a primordial black hole would be spectacular, releasing enormous energy in a tiny region of space. The explosion would produce a burst of high-energy gamma rays, showers of particles and antiparticles, and possibly exotic particles we have never seen. Telescopes could potentially detect these bursts. Several searches have been conducted using gamma-ray satellites, looking for the characteristic signature of a black hole explosion, but so far none have been definitively detected. The absence of detected explosions tells us something important. Either primordial black holes are very rare, or they formed with masses significantly different from the range that would be exploding now. This constrains models of the early universe. If future observations do detect a primordial black hole explosion, it would be revolutionary, providing direct confirmation of Hawking radiation and opening a new window into the physics of the very early universe. Another experimental frontier involves analog systems that simulate aspects of black hole physics. Researchers have created acoustic black holes in flowing fluids, optical black holes in special materials, and other systems where waves experience effective horizons. These analogues cannot perfectly replicate gravitational black holes, but they can test some of the quantum field theory predictions related to Hawking radiation. In 2010, a team led by Jeff Steinhauer in Israel reported observing analog Hawking radiation in a system of ultra-cold atoms called a Bose-Einstein condensate. By creating a flow pattern that trapped phonons, quantized sound waves, they observed spontaneous creation of correlated phonon pairs at the horizon, similar to the particle pairs in Hawking's original mechanism. While this is not gravitational Hawking radiation, it demonstrates the robustness of the underlying quantum physics and has generated excitement about what can be learned from analog systems. On the theoretical front, one of the most active areas is understanding the detailed structure of Hawking radiation and how information escapes. Recent work by Don Page, Jeff Pennington and others has focused on calculating the entropy of the Hawking radiation as a function of time. This is subtle because it depends on how you divide the quantum state into radiation versus black hole. The Page curve describes how this entropy evolves. Initially, as the black hole radiates, the entropy of the radiation increases because more and more particles are being emitted. But if information is preserved, there must come a point called the Page time, after which the entropy of the radiation starts to decrease, even though more radiation is being emitted. This happens because the later radiation becomes entangled with earlier radiation in a way that reduces the total entropy, encoding information about the black hole's interior. Calculating the Page curve precisely requires understanding subtle quantum effects, including what happens to the black hole interior as it evaporates. Recent work using tools from quantum information theory and holography has made progress on this, showing that gravity itself adjusts the entanglement structure in just the right way to produce a page curve consistent with unitarity. This is seen as strong evidence that information is indeed preserved, though debates about the mechanism continue. The firewall paradox has spurred intense research into the quantum structure of horizons. Some physicists propose that the equivalence principle really does break down for old black holes, that observers falling in would encounter a violent firewall of high-energy particles. Others suggest that the paradox arises from taking the semi-classical approximation too seriously, and that a full quantum gravity treatment would resolve it without firewalls. Still, others explore modifications to locality or new ways of thinking about quantum entanglement across horizons. String theory continues to provide insights into black hole entropy and information. By modeling certain supersymmetric black holes as bound states of strings and branes, string theorists have been able to count the microscopic states that give rise to black hole entropy. The counting matches Hawking's area formula exactly, a spectacular success that gives confidence that string theory captures important aspects of quantum gravity. Extending these methods to more realistic black holes remains a major goal. Loop quantum gravity, an alternative approach to quantizing space-time, also makes predictions about black holes. In this framework, space-time is built from discrete quantum units, and the event horizon consists of quantized area elements. The entropy comes from counting how many ways these elements can be arranged, again reproducing Hawking's formula under certain assumptions. Loop quantum gravity also predicts modifications to Hawking radiation at very short distances, potentially resolving the singularity. The holographic principle continues to reveal surprising connections between gravity, quantum mechanics, and information theory. The ADS-CFT correspondence has become a powerful tool for exploring quantum gravity in a controlled setting. Recent work has uncovered deep connections between space-time geometry and quantum entanglement, captured by the slogan "Space-time is entanglement." In this view, the smooth geometry we observe emerges from quantum correlations in the underlying microscopic description. This has led to fascinating ideas about quantum error correction and black holes. It turns out that the way black holes encode information on their horizons is similar to how quantum error-correcting codes protect information from noise. This suggests that space-time itself might be thought of as a quantum error-correcting code, with gravity emerging from the structure of this code. These ideas are still being developed, but have the potential to reshape our understanding of what space-time fundamentally is. Another exciting direction involves the role of baby universes and space-time topology. Some physicists speculate that information might escape black holes through tiny wormholes or topology changes that connect the interior to distant regions of space-time or even to other universes. These ideas are highly speculative and difficult to test, but they illustrate the creativity with which physicists are approaching the information paradox. The study of near-extremal black holes that are nearly but not quite at the limit of how much charge or rotation they can have, has also provided insights. These black holes have very low temperatures and evaporate incredibly slowly, allowing for detailed calculations of quantum corrections. They serve as useful theoretical laboratories for understanding how quantum effects modify classical black hole behavior. Observationally, the direct imaging of black hole shadows by the Event Horizon Telescope has opened a new era of black hole astrophysics. While these observations probe the environment near the horizon rather than quantum effects, they test general relativity in the strong field regime and might eventually constrain quantum gravity modifications. Future observations with higher resolution could potentially detect deviations from classical predictions. Gravitational wave astronomy has also revolutionized our study of black holes. The detection of merging black holes by LIGO and Virgo provides precise measurements of black hole masses and spins. While gravitational waves from mergers are classical effects, they might eventually probe quantum aspects of horizons. Some theories predict echoes or other subtle signals in gravitational waves that would indicate quantum structure at the horizon. Looking further ahead, several ambitious ideas could transform our understanding. One is to look for evidence of Hawking radiation in astrophysical data, perhaps through subtle statistical effects on the cosmic microwave background, or through the distribution of matter in the early universe. Primordial black holes, if they exist, could have affected the history of the universe in detectable ways through their Hawking radiation. Another is to develop quantum simulators, controllable quantum systems that can simulate aspects of quantum gravity and black hole physics. Just as quantum computers simulate quantum chemistry, future quantum devices might simulate the quantum mechanics of horizons, allowing us to test theoretical predictions in the laboratory without needing to observe actual black holes. There's also hope that cosmological observations might reveal clues about quantum gravity. The very early universe during the period of cosmic inflation might have been affected by quantum gravitational effects. If so, these effects could have left imprints in the cosmic microwave background or in the distribution of galaxies. Discovering such imprints would provide our first glimpse of quantum gravity at work in nature. The ultimate goal is a complete theory of quantum gravity that unifies general relativity and quantum mechanics into a single, coherent framework. This theory would tell us exactly what happens at black hole singularities, how information escapes from black holes, what space-time is at the Planck scale, and how the universe began. String theory, loop quantum gravity and various other approaches are candidates, but we do not yet know which, if any, is correct. What we do know is that Hawking radiation will be a crucial test for any candidate theory. The theory must explain where the radiation comes from, how it encodes information, what the entropy formula means microscopically, and how the apparent paradoxes are resolved. Any theory that cannot account for Hawking radiation cannot be the correct description of quantum gravity. The journey from Hawking's initial discovery in 1974 to the present has been one of continual surprise and deepening mystery. We have learned that black holes are far richer and more complex than anyone imagined. They connect to the most fundamental questions in physics, information, entropy, quantum mechanics, gravity, causality, and the nature of space-time itself. They serve as cosmic laboratories where nature operates at the intersection of the very large and the very small, where both quantum mechanics and general relativity are essential. As we look to the future, we can be confident that black holes will continue to teach us profound lessons about the universe. Each answer leads to new questions. Each solution reveals new mysteries. This is the nature of science at its best, a never-ending quest to understand ever more deeply how nature works. Hawking radiation stands as one of the great discoveries of 20th century physics, a beacon illuminating the path toward a more complete understanding of reality. Stephen Hawking, in finding that black holes radiate, opened a door to a new landscape of ideas that we are still exploring. His discovery reminds us that the universe is stranger and more beautiful than we imagined, that patient mathematical reasoning can reveal truths hidden from direct observation, and that the deepest mysteries often lie at the boundaries between different domains of physics. The story of Hawking radiation is not just about black holes evaporating. It is about the unity of nature, the power of human reason, and the endless capacity of the universe to surprise us with new wonders waiting to be discovered. As we conclude this 3-hour journey through one of physics' most profound discoveries, we are left with a sense of both accomplishment and anticipation. We understand so much more than we did 50 years ago about black holes, quantum gravity, and the fundamental nature of space-time. Yet the deepest questions remain open, challenging us to think harder, to develop new mathematical tools, to imagine new possibilities. The quest to fully understand Hawking radiation and its implications continues. The next breakthrough might come from a theoretical insight, from a detection of primordial black holes, from gravitational wave observations, from quantum simulations, or from a direction we have not yet imagined. Whatever form it takes, we can be sure it will deepen our appreciation for the elegant and surprising ways that nature operates at its most fundamental level. The universe has given us a puzzle in the form of black holes that radiate. Solving this puzzle completely will require combining our deepest theories in new ways, perhaps developing entirely new frameworks for thinking about space, time, matter, and information. This is the work of physics, and it is work that continues today in universities and research centers around the world. Every physicist working on these problems stands on Hawking's shoulders, pursuing the vision he opened up of a unified quantum description of gravity and space-time. So we end where we began, with a mystery. But now it is a mystery illuminated by understanding, a puzzle whose outlines we can see even if we do not yet know all the pieces. Hawking radiation has shown us that black holes are not the end of physics, but a new beginning, a gateway to deeper truths about the nature of reality. The journey continues, and the destination promises to be as surprising and magnificent as everything we have discovered so far.